Before we start the next section, I did post a exam 2 review on Blackboard. That should not send any alarms through your system because the exam is still off a couple weeks, I think. Maybe exactly 2 weeks. 1, 2, 3, 4. I think that's right. I could be wrong. But it's a ways off. You can check your syllabus and I'll check my schedule as well and update you. But it's not imminent. It's not happening anytime soon. I just wanted you to have the review so you can start looking at it. So maybe if that's in your head and those bullet points are in your head as you go through during the lecture and you hear me say certain things, you might put a little star in your notes and remind yourself that this is important. It's on the list. It's going to be on the exam, and I should emphasize that. Okay, so some of these things that will certainly be on the exam and probably on a quiz we'll have between now and then, probably sometime next week, which I'll update you on that. It won't be Tuesday. Well, actually Tuesday might be a good day for a quiz because we could do this material before we start into the next section. Actually, that's not a bad idea. It's my first good idea of the day. Hope it's not my last. Okay, we did, what was the last quiz we did? 3? I think so. That feels right. Because we had the first chemistry quiz, then did we have cell anatomy? Wait, was there one in between?
The first one we had was, hold on, I have it in my notes.
Well, in any case, the last one was number 3, so this will be quiz number 4. If I'm wrong, that's okay. We'll call it 3. But
Oh, the other one was of the macromolecules. The one that you-
the macromolecules, all right. Well, now I'm feeling insecure about the number.
No, it's 4.
I'm just gonna say quiz Tuesday. We'll sort out the numbers later. 3 or 4, it doesn't matter. But in any case, here's what we'll do on that quiz. Let's make it about this chapter. So we'll do some osmosis questions. So you'll want to know what it means to be isotonic, hypertonic, hypotonic. If I give you either a diagram or a description of a solution relative to the solute in the cell, you'll want to be able to identify which of those 3 groups it is. I'm sure you will want to know the types of transport. And this actually has several subcategories, so we would want to know diffusion, facilitated diffusion, and we would want to know that these are passive transport. You would want to know there's also active transport. And active transport comes in 2 flavors. We had, find it here, primary active transport and secondary active transport. So I'll put a primary and a secondary. Okay, so that looks like 1, 2, 3, 4, 5, 6 or 7 questions right there. So to round it out, we could use our very specific example of the sodium, potassium ATP pump, or ATPase pump. Probably get 3 or so questions out of that. Okay, so that'll come out to be a nice little 10-question quiz. And I'll take a picture of that so I don't have to write it all down. Apparently when I write notes, I lose them. So I will save myself the trouble. Okay, so now having said that, let's briefly review this stuff and then we will boost ourselves into the next set of material, which is going to be energy and reactions and enzymes and aerobic respiration. So let's briefly review. The concept of osmosis, remember, is the movement of water, and the movement of water is determined and guided by the amount of solute inside or outside of a cell. So we can have water that leaves the cell causing shrinkage. We can have water that goes into the cell causing osmotic lysis, where first we have a slightly different effect when the cell is constrained by a cell wall. So if we take a plant cell into consideration, the cell can still shrink and swell but it's not going to burst when it swells, and it's not really going to change too much when it shrinks, other than not having pressure on the walls of the cell, wall. Not having pressure pushing out on the cell wall will cause a plant to wilt. And if we have pressure pushing out, it will cause the plant to be more firm or stiff. And so that's a different effect than it has if we don't have a cell wall, right? So the plants, bless you, certainly have an advantage on us in that regard. Now, why water would move in one direction or another, remember, has to do with the solute concentration. So if we have a cell where the solute concentration is equal on the inside and outside of the cellular membrane, plasma bilayer, the phospholipid bilayer rather, then water may move, but there'll be no net change. So if a little goes out, then a little will come in, and it will break even in the long run. If we have a solution where there's a higher degree of solute on the outside than the inside, then water is going to tend to go in the direction of the higher solute concentration. So that's a hypertonic solution, and water will leave the cell. Okay? If the cell has a higher concentration of solute than the outside, then water will tend to, again, go in the direction of the higher concentration. So if a cell is in a hypotonic solution, water will want to cross in. Okay, think about too, we're thinking about this in the context of our cells as organisms sitting here in the classroom where we have somewhat of an aqueous environment surrounding our cells, as well as an aqueous environment inside our cells. But imagine if you were an aquatic organism. Then osmosis really becomes quite an issue, because if you are a fish, for example, you can't just swell up all the time because you have a higher solute concentration. So when fish live in different environments like fresh water and salt water, they have to really fine tune their solute concentrations to regulate the osmosis, which is a constant environmental pressure on them. And think about fishes that go from salt water to fresh water, like migratory fish like salmon, the complexity that they must face biologically trying to regulate that. One of my friends who's a fish enthusiast and actually has a degree in fishery science said that the reason you add, well, let me ask you this. Have you ever added salt to a freshwater aquarium? Does anyone keep fish these days? That's still a thing? I fish most of my young life. Well, if you have freshwater fish, they suggest you add a small amount of salt, of aquarium salt, to the water, which for me seemed counterintuitive, because why would you put salt in a freshwater tank? And my friend said the reason you do that is because it de-stresses the fish. And if there's a slight amount of salt concentration in fresh water, it reduces the amount of osmotic work that the fish has to do to keep the pressure of water equal on the inside and outside of its cells. So it takes away some of the energy that fish has to expend. I thought that was pretty interesting. Of course, you can't just put a freshwater fish and toss it into salt water and say, here you go, don't worry about it anymore, your stressful days are over. There's a limit to what they can handle, obviously. Okay, practical information you can use. All right, let's keep going down our list real quick. So the idea of, well, this won't be on the quiz necessarily, but the idea of the conformational change is going to be important, especially as we go into the next chapter to talk about enzymes. And the idea of a conformational change is that a protein can change its structure to accomplish some task. This can be catalytic, or it can be simply moving something across a membrane. But the conformational change is a structural difference between one form and another. Okay, in this case, it's creating a pocket where something that cannot cross the phospholipid bilayer on its own has this happy hydrophilic space, and then when it switches out, it goes from one hydrophilic section outside of the cell to its little hydrophilic hiding space to the hydrophilic space inside the cell. So it totally escapes interaction with the fatty acid tails, which are hydrophobic. Okay, then the types of transport, this is a component of that. Whether or not things are coming into the cell alone, like a uniporter, whether they're coming into the cell with a friend, like a symporter. Remember, sym means like to work together. And then the other possibility, which is the primary case in our sodium potassium ATPase pump, is when one thing comes in and another thing goes out. So we've got these two ships passing in the night. We call that an antiporter. Okay, the types of, oh, I didn't do diffusion, let me back up. The types of diffusion, if the word diffusion is in our statement, then we're talking about passive transport. Because diffusion, by definition, is the movement of molecules from areas of high gradient to low gradient. Okay? So they're trying to go down their concentration gradient until everything is equal. So this doesn't require energy. The only time we have to intervene is if moving from high to low requires crossing something that they cannot cross. So if we're talking about something like oxygen moving back and forth across the phospholipid bilayer, nothing is required. Oxygen is going to go from high to low concentrations. So when you pump red blood cells to your tissues and they have a high oxygen concentration, when they get to your tissues that don't have oxygen, that oxygen flows out into the space of lower concentration. And then the carbon dioxide, which is at high concentration in your tissues because you've been doing work, that goes into the red blood cells, which has a lower CO2 concentration, and then goes, eventually, you exhale that CO2. Sometimes, though, a molecule can't cross without help. This doesn't mean energy is involved necessarily. This just means you have to provide a way for it to get from point A to point B. So that's facilitated. And then if we're going against the gradient, if we're going uphill, then we're going to require energy. And this is going to be true in many of the cases, many of the examples we're going to talk about this semester. Okay. Then active transport, again, go back, fast forward here. Active transport can come in two forms, primary or secondary. The main difference being primary is directly using an energy source like ATP. Again, I don't think we'll use another example that does not use ATP. I think it will always be ATP in this class. But a primary energy source that pumps something against this gradient. Secondary active transport then utilizes the gradient. Okay, so it's utilizing the gradient of one thing to do work for another. In this case, this is a real example. It's using a proton gradient, which is hydrogen ions at high concentration outside of the cell. Those hydrogen ions have a way to get to the other side, and it's through this transport protein. Along the way, as the transport protein is moving the hydrogen ions, these sucrose molecules are going to stow away in here and go along for the ride. So the energy is not directly being used to move the sucrose, but the gradient that resulted from the energy is. So that's secondary active transport. And then our final example that we did right before, I guess, we had exocytosis and endocytosis, but I'm not going to put that on this quiz. We have enough. But the final example was the sodium-potassium ATPase pump. And this is kind of a model operation for how the cell creates gradients using an antiporter. And this, as far as I know, this was the first one that was really well studied and well understood. And so it still serves as a great example. And what it's trying to do is create a gradient where you have more sodium on the outside and more potassium on the inside. But in addition to that sodium-potassium difference, you are moving things unequally. So since sodium and potassium both have one positive charge, if you were just trading places, you would break even, right? Nothing would change. But you're not just trading places. 3 sodiums go out for every 2 potassiums that come in. All right, so because of that, over time, if this was the cell where this was happening, over time, the amount of positive charges on the outside would greatly outnumber the positive charges on the inside. And so that's an electrochemical gradient, right? Because not only is it a gradient of a particular atom, an ion in this case, it's also a gradient of charge. So that's an example of the electrochemical gradient, which is a useful thing because this cell can do work with that. Okay, it can transmit, in this case, like a neuron response, an action potential. Okay, so the way it works, remember our enzyme has 2 forms. It has a form that we call E1, and it has a form that we call E2. These are the 2 conformations. So this example of the sodium-potassium ATPase is going to go through a conformational change to do its job. So the conformational change comes when a phosphate is added. And that phosphorylation event is triggered by the binding of 3 sodiums into their little sodium binding sites. Okay, so these are sites in the enzyme where there's a puzzle piece fit so that the sodium ions are going to bind, but other ions aren't. Okay, it's the right size and the right shape and the right structure just to bind sodium. When they bind, the protein becomes phosphorylated by ATP. We'll learn a lot more about ATP today. The phosphorylation event causes the protein to undergo the conformational change. After it changes, those are no longer ideal sodium binding sites. So the sodium has no affinity now. Sodium just floats away. It leaves, it diffuses out. However, the change does create two ideal potassium binding sites. So now those guys bind, and when they bind, that triggers the dephosphorylation of the enzyme. So our little inorganic phosphate pops off there. And without the phosphate, we go back to E1. And in E1, this enzyme doesn't want anything to do with potassium. It only wants sodium. So we're back where we started. So for every ATP molecule, we can pump 3 out and 2 in. Okay? All right, so that's your quiz in a nutshell. And then, yep, okay. Questions? Comments? Encouraging words.
I believe